All right, folks. So just want to look at heat equation, what the book calls problem 2. Just a reminder to all of the viewers that we've got exam 1 coming up next week on Thursday. So please take a look at Canvas for review materials and information about that. So you've actually done this problem in your homework. And so I tricked you into learning. Here, this PDE has these so-called insulated boundary conditions. So it's the same heat equation that we know and appreciate. It's the same initial condition. The only difference now is here, and these boundary conditions should be now familiar to you because you did it on the homework, is we have here the partial of u with respect to x at 0, which is the left end of the rod, and partial u with respect to x at capital L, which is the right end of the rod, for all time must be fixed at 0. And so, how do we interpret that? Certainly we can interpret that mathematically, but how do we interpret that physically? Fourier's law of heat conduction, so this is good review of the concepts, right, everybody? So Fourier's law of heat conduction says the heat flux is proportional to the temperature difference, with respect to the x variable, the spatial temperature difference. So here, if we make partial u partial x equal to 0, then there's no heat flux at the ends of the rod. And so there's no heat flowing at the ends of the rod. And so, we interpret that, this no heat flow, as being that the ends of the rod are insulated. Okay, so at the ends here. So, in the original heated rod problem, the heated rod, the lateral sides are insulated anyway. And now in this particular case, so these are called Neumann boundary conditions. In this particular case, where the partials are 0, we have the whole thing is insulated now. Okay. And here, we expect there to be a steady state. And I don't know if I meant to say, since there's no internal source of heating, there could be potentially some kind of internal source of heating, a chemical reaction or something that could affect the long-term heat. But here in our equation, there's no plus Q. And so I'm going to assume that the solution has this traditional form that, we've been doing here, that it has a steady state portion that's not dependent on time. This is the long-term behavior of the temperature, plus what we call the transient solution. This is a function dependent on space and time. And this is the, more short-term time-dependent behavior of the temperature. And we expect, as t goes to infinity, the transient solution to go to 0. That's just our theory of how everything should work. And so one thing I want to show you, rather than solve this right away, because as you know, the set of functions that satisfy the PDE and these boundary conditions. So for now, we forget about the initial condition. We use the initial condition last. The set of functions that satisfy the PDE and boundary conditions form a vector space. And so we can directly start doing separation of variables, But before I do that, I just want to show you, how do we translate this condition if we were doing traditional separation of variables? I just want to show you, how do we translate that boundary condition to U bar when we do that very traditional type of separation of variables? So let me show you that first, but then we'll actually, just solve it directly. Okay. So here, let me work out the left-hand side and the right-hand side of the heat equation separately. So partial U, partial T, I replace U with U bar plus V. And U bar is not a function of T. So this is equal to 0 plus, partial V, partial T, or just partial V, partial T. And on the other side of the equation, I start with the second partial of U with respect to X. Once again, I'm replacing U of xt with U bar plus V. Here, both functions are functions of X, and we can use the linearity of the derivative and distribute the derivative to each term. So we have a regular derivative on u bar and a partial derivative on v, which is a multivariate function. So now let's put together the heat equation. So here, I'm going to do something slightly different from what I did last time, because I just want to show it to you in a different way. I'm going to bring this term here that's on the right-hand side, I'm going to bring it over. Okay. Set it equal to 0. Now what I'm going to do is replace each of these parts with what we calculated up here. So I'm going to replace partial u, partial t with partial v, partial t, and I'm going to replace this second partial with respect to x with u bar double prime plus partial, second partial of v with respect to x. Okay, so here I replace partial u, partial t with partial v, partial t, copy down the minus k, and then plug in, u bar double prime, the second partial of v in for the second partial of v with respect to x. And here, this is pretty straightforward. So now I'm going to now just assume each of the parts. Oh, sorry. So here, let me now rearrange this. I'm going to pull out this term. So here, I'm going to distribute the minus k and write this term out in front. I want all the partials of v with each other. So there's the minus k u bar double prime. I distribute the minus k, pull it out in front. Distribute the minus k. Don't forget here, I'm going to also distribute the minus k to the second partial of v, and then move the partial v, partial t next to it. And so now, one way I like to think about it now is, okay, so now I'm going to let this part be equal to 0 and let this part be equal to 0. And that gives me my two equations. So I have, here's equation 1, and then here's equation 2. Set them each equal to 0. And here on this minus ku double prime of x, you can divide both sides by k. And so here is the, ODE and PDE for the steady state and transient, okay? And so now, as you know, we should find boundary conditions and for both, and initial conditions for the PDE. So this is the part I want to show you that's a little bit different. Okay, so all that other stuff, hopefully, is familiar to you. So if we go back to this boundary term, remember here, partial u, partial x, the u I replace with u bar plus v and distribute the x, distribute the derivative, excuse me. And so we get u bar prime plus partial v, partial x, okay? So now we look at the boundary conditions, because our boundary conditions are on this type of term, right? This partial u, partial x. So that's why I calculated that. So here we have these trivial Neumann boundary conditions. And so I'm going to now replace, this with this. And, the x gets replaced with 0. So that's what I have right here. U bar prime of 0 plus partial v, partial x at 0 comma t has to equal 0. And then do the same thing, but for the other side, right? So now for this side, do the same thing. I'm going to replace it with this and plug in a capital L for the x and set it equal to 0. So let me show you now. This part here is slightly different. And so just kind of follow along first, and then we'll think about why we did it this way, okay? So we set these two boundary terms equal to each other. And what I'm going to do now is bring all these terms over. So I get u bar prime of 0 minus u bar prime of L and partial v partial x minus at 0 minus partial v partial x at capital L. So now let me show you. So now we're gonna piece it out, okay? For the boundary conditions for v, we're going to choose them to be trivial. That's for v, that's for the transient PDE. And so the question is why, and everybody knows what I'm going to say, because now the set of functions that'll satisfy the PDE and the boundary condition form a vector space. I've never said that before. Never. It's a new concept to me. Okay, so here we set these characters equal to 0 because we can. Why? Because we can. Because it's helpful, Just like when we do a U substitution, you make one choice and not the other. So here we set them directly equal to 0. Okay, here's the part that's different, that might be unexpected. Okay, so let me be very explicit about this. So look, when we set partial v at 0 and L equal to 0, this term disappears completely. And now we have the equation u prime of 0 minus u prime of L equals 0. Okay? And that's the equation we use as our boundary condition. We don't set each of these equal to 0. And so here what I then do is I move one term over and write it in that form. So then here I move the u to the other side and write it in this form. So one reason for doing this is because we want to keep this as general as possible. Yes, we could set them equal to 0. The equation would be true, but there I feel like we're assuming too much. Ultimately, we want to preserve the mathematical generality. And strictly speaking, if this is the case, then this term disappears. And there's no need for us to assume any more. What's left over is a perfectly good boundary condition. What's left over now, well, let me just use that. I don't want to assume more than is needed. So this is purely about, being careful and maintaining generality here. We're only assuming what we need to assume to make this work, So yeah, that's the one thing I wanted to show you, that when you do the separation here, you get a different type of boundary condition on the ODE. And of course, for the initial conditions, we just do it the usual way. You can solve for v of xt. Remember, u of xt equals u bar plus v. So here I just solve for v of xt. And then I plug in a 0 for t. And we're given that ux of 0, this is given in the PDE that ux of 0 is f of x. And so we get our boundary condition, our initial condition here, our initial condition here for v. And so for v, we have the initial condition, we have the boundary conditions, and we have the PDE, so that's a complete system. And for u bar, we have the ODE and boundary conditions. So here's the steady state ODE for this case where we have the insulated boundaries on the rod. And here is the transient PDE with homogeneous PDE and homogeneous boundary conditions, so that the set of functions that satisfy the PDE and boundary conditions form a vector space, so that we could start to do separation of variables now directly on V. Okay, here I only did this as an exercise to show you what the separated equations would look like. in actuality, the original PDE and trivial boundary conditions already satisfy a vector space. We can just actually do separation of variables on U, the original variable U. Okay, so here, I wanted to show you in particular what happens with this boundary condition. That's different. And that's because of the our Neumann boundary condition. And so now one option now would be to solve each separately and put them together as we've done in the past. Actually, but here I say that actually, since the original PDE and boundary conditions with respect to the original variable already form a vector space, let's just do it directly and save ourselves. We don't need to. So it was kind of, I just mainly wanted to focus on what happens to the boundary condition in the Neumann case. Okay. So I hope we're okay. I hope all that theory is making sense to you. You can do one or the other, but here I'm going to take the path of least resistance. So let me just solve the original problem since it's an option. So here we're going to make the traditional separation of variables assumption with, it being not trivial being an important part of the assumption. And you know how the song and dance goes. We're going to take this and plug it into the heat equation, right? And then you get your old time domain problem and the boundary domain problem. But this time, be very careful here, from when we had our Dirichlet boundary conditions, here these boundary conditions are different. These now is, with the Dirichlet problem, we had f of 0 equals 0 and f of L equal to 0. That's when we had steady boundary conditions and the sides were fixed at 0. Here now it's f prime of 0 equals 0 and f prime of L. So that's a direct result of these different kind of boundary conditions. And so with the time domain problem, as always, you get this exponential solution that depends on lambda. So we have to keep track of lambda now. In the boundary value problem, we'll see there's more than one lambda. So we'll get more than one time domain problem, one for each lambda, which we can coordinate with the solutions of the boundary value problem and then put them together to create the product solution. So if lambda is less than 0, we get a trivial solution. I'll let you think about that. So on the slides that I put out for Wednesday, I work out the case lambda less than 0. If lambda is equal to 0, here, you should actually not go to, you should just go back to the original ODE. If lambda is equal to 0, then f double prime equal to lambda fx just becomes f double prime equal to 0. And then you integrate that twice and you get f of x equals ax plus b. The first integration gives you a constant. The second integration, you get constant times a variable plus another constant. And so the boundary conditions, when you take the derivative, when I take f prime, the x plus b part disappears. And then when I set it equal to 0, you get a is 0. But the derivative at the other end doesn't tell us anything because when you take the derivative, the b disappears. So here when lambda equal to 0, we actually have a non-trivial solution. It's a constant. We know from our physical analysis, this kind of is fitting because we expect there to be a steady state solution. For lambda greater than 0, so this is all good review for, just the test and just the material. It's not focused. It's about learning, right? So to solve the eigenvalue problem, when lambda is greater than 0, we let f of x equal e to the rx. Okay, so I hope, this is like boring you. Okay, and then you get the characteristic equation, r squared e to the minus lambda. Technically, you can write the solution in this weird complex form, but we use, we're trying to use waves here. So we use Euler's formula to rewrite the solution as cosine plus sine. And you don't have to explain this every time when you're solving this problem on a test. When you're doing this lambda greater than equal to 0 case, whatever, you don't have to explain this. I personally am fine if you say, in this case, we know this is the solution. Are you with me, folks? So you don't have to, I ran through the details of it because I want you to kind of, keep in mind how we got here and we use Euler's formula and all this stuff. but you don't necessarily need to, you know. I'm okay at this going right to cosine plus sine, you know. So now boundary conditions. Here, when we take the derivative, this cosine will become a sine and this sine becomes a cosine. You know, this flip-flop happens. And of course, it's a chain rule. And so I have the derivative of the outside would be minus sine root lambda x times the derivative inside would be root lambda, and then we still have the constant. So there's the root lambda, there's the derivative, there's a constant and the minus sign, and then I plug in 0. So here, that first term disappears. Sine of 0 is 0. Cosine of 0 is 1. I get C2 has to be 0. Our solution f of x here is just looking like, you know, this part disappears. And so it's just looking like a cosine family. And apply the other boundary condition. Again, we take the derivative, the cosine becomes a sine. Plug in capital L for the variable. Set it equal to 0. So you know, here's one thing I didn't really explain before. Why do I not say C1 can be 0? I never explained that before. Well, we know C2 is 0. If C1 is also 0, then F is trivial. If F is trivial, our solution, F times G, is trivial, and our first assumption of separation of variables is that we don't have a trivial solution. So in this case, if this product is equal to 0, it's not possible for C1 to be 0. Otherwise, we would have a trivial solution. So here, the rest of it, the terms other than C1 have to be 0. That is, you know, and then you can divide both sides by square root of lambda. We already did the case lambda equal to 0. So that's how I know we already did the case lambda equal to 0. So here I know lambda is not 0. So the only thing left is this term right here, sine root lambda, that has to be 0. I don't know if I ever, you know, went into the details there. But that's the only possibility. Otherwise, we end up with a trivial solution. And we know sine, you know, we know root lambda L has to equal n pi, that sine is 0 at integer multiples. And so root lambda L equals n pi. So root, divide both sides by L, root lambda equals n pi over L. And here, there's no n equal to 0 because I already handled, if you let n equal to 0, that makes lambda equal to 0. And we already dealt with the lambda equal to 0 case. N can be plus or minus 1, plus or minus 2. But remember, sine is an odd function. So sine of, let me just say n for now, not to write too much. Sine of negative n is minus sine of n. So what does that mean? It means that these are scalar multiples of each other. So they're linearly dependent. We don't need both. You can take one or the other. So I'm going to just take, you know, just let me keep the positive terms of the n. So I have lambda sub n. So now look, I put a subscript on here because lambda is now essentially a function of this parameter n. And look, I've dropped the negative terms here. N is now just 1, 2, blah, 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 because sine is an odd function and it would be redundant to keep. You know, if you wanted to be, in theory, we could have kept the negative ones, right? But why be difficult, you know? But yeah, so I hope you get these little details. And so now, you know, we can create what's called the product solution, right? So I can take the solution to the time domain problem and multiply it to the solution, sorry, the solution to the space domain problem and multiply it to the time domain problem. And here we've replaced lambda. So, you know, don't forget here I had root lambda x, and here we had minus lambda kt. Then we found out there wasn't just one lambda, there's n of them. So this become a lambda sub n. And then we actually solved for it. Now here, I want you to, pump your brakes for a second and think about this, that each one of these, we haven't verified it, but we can, each one of these satisfies the PDE and the boundary conditions. So, we already have, each one is a solution. Any finite combination will be a solution. And then we have infinitely many, so now, we literally have found infinitely many solutions. And typically the very first term, is part of that, what we call slowest decaying approximation. So now, yeah, we cobble together all of the solutions because we want one solution that, at least mathematically, from a pure math point of view, not necessarily an applied math point of view, from a practical point of view, we're going to drop the terms, some terms, right? Using superposition principle, we combine all the terms together, pulling the lambda equal to 0 term out in front by itself, because there the eigenfunction is just a constant. So here, just kind of out of human tradition, we've separated, a sub 0 just because it's a constant by itself, and all the other terms have functions that are, functions of either x or t, or both actually, right? So this is what our superposition solution looks like. And this has been mathematically reverse engineered to satisfy the PDE and the boundary conditions. The last part we need is to get the initial conditions. And the cosine functions on 0 to L, you will see and you will show, and that we've talked about, form an orthogonal basis. So on your homework, I'll ask you, just by way of review, I think this is homework number 6, I tried to set it up to be like just to review some of the concepts to get you ready for the test. You'll show these integral equations. It's not difficult at all, right? It's like just using the identity, the trig identity. And so we have an orthogonal basis. And so when t equals 0, we get what's called a Fourier cosine series. And we can use the orthogonality. Okay, so we've talked about this many times before and done it on homeworks many times, right? Use the orthogonality and projection formula, right? We talked about the projection formula to find a sub 0, is the average of the initial temperature, and a sub n has this formula here. So that's kind of the full story, so you should think about, when I have a heat equation with trivial Dirichlet boundary conditions, I know now that's going to be a sine series from the work we've done here, if it's 0 to L. I know if I have a heat equation with a rod from 0 to L, and the boundary conditions are, partial u, partial x at 0 and L equals 0, I know that's going to have a cosine series. You can start to just read the PDEs without having to do the work. So you'll see on the homework, I've asked you to solve some PDEs without calculating any integrals. You can see from the form, the cosine series or sine series, and then using orthogonality, depending on what the initial condition is, you can find the series representation very easily. Okay, so I hope that'll be a good theory review. So, of course, now that we've got this formal solution, we have all the usual issues that we tend to talk about, right? Convergence and all that kind of stuff. So for the convergence issue, it's not that much different. I mean, to me, it's not different at all from the sine series. So here, the first term is constant. So don't even worry about the first term. If you have something that converges and you add a constant to it, then it's still going to converge. Okay, so here, let's just talk through the analysis. Don't worry about a sub 0 for now. So now what we do, we want to show this thing is absolutely convergent. We take the absolute values here. And then I can bound this. I can say this is less than, and put in absolute values in here for each term. And you can drop the absolute values on the exponential term if you want. The cosine term, what I can do to the cosine term is bound this term away. I'll make the cosine term, say less than or equal to 1. So I have a 1 in here. And as before, this is a decaying exponential term that goes to 0 very quickly. So the only problem with convergence would be from a sub n. And a sub n, that's from the initial condition. A sub n is the 2 over L integral 0 to L f of x times cosine blah blah. So a sub n, and cosine's well behaved. So it all comes down to our initial data f of x. And so again, if our initial data is well behaved enough, if it's not too, has infinite discontinuities, I mean, whatever, even if it has infinite discontinuity, might as well try it. But yeah, if it's a well-behaved piecewise smooth function, then we should be able to at least get convergence for the absolute convergence for the full-on series. And I won't do the verification, but you can also verify that this does satisfy the PDE. It's basically, it's just kind of does a flip-flop with its derivative, so everything kind of works out. So here's the full solution with everything plugged in. So this is a sub 0, and this is a sub n. And as long as this function f of x is well behaved, convergence should be fine. All the other terms can either be bound by something that's finite or are decaying to 0. And then once we have piecewise smooth, the Riemann-Lebesgue lemma kicks in. The oscillatory cancellation tells us these coefficients go to 0 fast also. So, and we can also take the, for the steady state, we believe that there was a steady state solution. So, this part is us verifying that our mathematical world that we've created, our simulation of reality, is behaving like reality. On a couple of slides ago, we proved that when we had insulated boundary conditions, we used physics to show from the physics point of view, insulated boundary conditions would imply that the steady state solution would have to be the average initial temperature. And so now we're able to mathematically verify that through separation of variables. So this is confirmation that our artificial world that we've created using equations is behaving the way we hoped it would. From this simulation world, we do our engineering and then put that object in the real world. As before, for large but finite time, because these terms are exponentially decaying, the larger n is and the larger t is, the smaller that term is. So we have what we call this large but finite time or slowest decaying term approximation, where we just use the first term of the series, not just a sub 0. That's not, that wouldn't be good. We use a sub 0 plus the very first term of the series. Can you use more terms? Of course. This is just, a kind of baby steps. Let's start at a simple place for a simple approximation. And then that's a very nice function to work with, in terms of doing math. And so this would be the approximation. I just plugged in all the little values for a sub 0 and a sub 1, just so we could see the solution in its full dress uniform. So there's the full. What you should notice is the only place we have variables, right here we have an x variable, and right here we have a t variable. And we've mathematically kind of decoupled the behavior in space and the behavior in time and related that to the behavior in temperature. And so conceivably you can analyze one or the other. How is space affecting temperature? How is time affecting temperature? And how important temperature is to engineering. So that's the solution to the heat equation where we have insulated boundaries. And you solve this problem for the case where capital L was equal to pi. My hope was to make you discover it yourself rather than you just watch me do it and then you repeat what I did, because you had all the math necessary to do the problem yourself. Okay, so my hope is, when you saw this was just a review of everything you've done, and there's nothing here that looks weird to you. So I just want to now finish up with a technical discussion of what the heck is this Fourier cosine series thing that we ran across. I want to go back, and I think it's really important to keep this in mind to prevent confusion. When we started this class, and when we started studying Fourier series, we studied it on the interval minus L to L. And so that's what's different here. For the heat equation with this, steady trivial boundary conditions, and for the heat equation with these trivial Neumann boundary conditions, we're on 0 to L. And so this problem we'll talk about on Wednesday. So we'll do the heat equation on a ring, okay? And I'll show you the geometry there. So that's the main difference. You should start at that point, that when we started this class, the kind of Fourier series we're used to is the kind that's defined on minus L to L. These are two special cases of this. Okay, so let me show you. Just like the Fourier sine series is a special case of the regular Fourier series, I'll show you the Fourier cosine series is a special case. Okay, so here we define, one thing to remember here is that a cosine series, a sum of cosines, is going to be an even function. So whatever it's representing has to be even. So we define what's called the even extension of f. So f sub even, and it's defined to be just the regular function on the domain 0 to L. Now we're going to extend the definition here and define, the function on negative L to 0 to be f of negative x. Think about it geometrically. If I have some f of x, replacing the x by minus x just reflects it, and you end up with an even function. So the even extension of f of x, by definition, by construction, is itself an even function. F of negative x here equals f of x for the even extension. So now we have the language now to describe what the Fourier cosine series representation of a function is. So suppose we can write f of x equals this Fourier cosine series here, where the original function f is defined on 0 to L. Then we should notice the right-hand side is continuous, even, and 2L periodic. So I hope you know what I'm going to say, that the right-hand side represents the periodic extension of this even extension of f of x, and it's been adjusted. That is to say, wherever there's a jump discontinuity, the function's redefined to be the value at the average, and wherever there's a removable discontinuity, that's been filled in. And this is because the right-hand side is the continuity smoothing properties of Fourier series, which we talked about, weeks ago. So in notation, the Fourier cosine series of f represents this horrible mess. You start with f, so start with f right at the core. Start with f, then we do its even extension, then we adjust it, then we do the periodic extension. Okay, and how, in general, the Fourier cosine series of f can be thought of as just the regular Fourier series of the even extension of f. Here's a picture. So I start with, and I'll stop after this, I'll start with x defined on 0 to L. And suppose we have the Fourier cosine series of this function. We use the projection formulas and use integration by parts and calculate a sub 0 and a sub n. So here's what the Fourier series would converge to, based on our theory. So start with the original function, create what's called the even extension by reflecting it about the y-axis. Now I have a function defined on minus L to L. Take the Fourier series of that function. Whoops, what happened? Take the Fourier series of that function, and boom, you get, the Fourier cosine series of the original function f, or the Fourier series of the even extension of the function f. And here, all the smoothing's been done, right? All the removable discontinuities have been smoothed over. In this case, there are no jumps. And we can compare and contrast with a Fourier sine series, which is the Fourier series of the odd extension of f. Start with the same function f, do the odd extension, flip it about the y-axis and x-axis. Now we have a function defined on minus L to L. Take the Fourier series of that, and that's the Fourier sine series of the original function f defined on 0 to L, or this is the Fourier series of the odd extension of f. And here we've done at the removable discontinuities, those have been filled in. At the jump discontinuities, the functions redefined to be the average. So I hope all that material today was more, was essentially review for you. And on Wednesday, we'll talk about heat equation on a ring. Okay, and we'll have, so how is this different from a rod? With the rod, the ends aren't in contact. So now what I want you to imagine is you grab the rod and bend it using, APPM math strength. Wielding pencils gives you pythons. Okay, anyway, we bend it into a ring, and then, game on, heat equation, what are the boundary conditions, blah, blah, blah. Hint, there might be separation of variables might be involved. All right, folks. So that's my time for today, and I'm on schedule. I'll send you the lecture slides for Wednesday. Please take a look at the old tests that I posted, and everyone take care. And I'm going to stop right now.